Ok. Faire des heures
Je ne sais pas si ça va marcher. Donc là, on a une situation ubuesque. Le jury est en ligne.
Ouais, et les superviseurs.
Et les superviseurs.
Sont seulement à moitié là. Hello Rick. Sorry, we are waiting for the rest of my supervisors. They are having lunch, and it's quite a big thing in France.
Donc si Benoît est là, c'est qu'ils ne vont pas tarder.
Je l'avais nickel.
Ok, parfait. Merci beaucoup pour la gestion.
Un peu de risque.
Le serment du doctorat.
Alors, ça c'est bon.
We are waiting for Jean-Marc. We are still on time.
Est-ce que tu peux m'envoyer, me transférer un mail où il y a tous les membres du jury qui sont dedans?
Page de garde.
Luc, ça t'embête avant que Jean-Marc arrive que je parle un tout petit peu avec tes...
De toute façon, il
Ah, voilà. Okay, do you hear me remotely?
Yes.
Okay, great.
Yes. Hi.
So I have the great honor to be president of this jury. I will present everybody to the audience soon. I just wanted to tell you a few things because I'm not sure that you already participated to a jury in France. So the way it works is the candidate has 45 minutes to present his work. And after that, there is a question session, which lasts an hour and a half. So each member of the jury, starting from the reviewer, will ask question. Usually you ask the whole bench of question at the same time. And yeah, it's about 20 minutes. Well, there is no real limit of time. So if you want to take more, you can, but it's about 20 minutes per jury member, the time to ask question. And yeah, it can be less, of course, but we try not to make it more, otherwise it's very long afterwards. And after this questions, we will meet in a room where there is no public audience, and we will deliberate, so decide whether we believe, sorry for you, Luc, usually we do that before. so to decide whether he deserves to be to get the PhD grade or not. And yeah, that's it. Do you have particular questions?
No, thank you.
No? Okay. So I will present the jury members. Thank you for the slide. It will help me. So welcome everybody to this defense about this software variability for resilient performance model for configurable systems. We're going to hear Luc Lesoil. And there are two reviewers for this thesis, which are Lidia Fuentes, who is professor at Universidad de Málaga in Spain, and Rick Rabizer, who's a full professor at Johannes Kepler Universitat in Austria. And then there are two examiners, three, including me. One of them is Maxime Cordy, who's a research scientist at University of Luxembourg, and Pouyan Jamshidi. I hope I'm not making a very bad thing of your name. And who is assistant professor at University of South Carolina, in the US. And myself, I'm Elisa Fromont, and I'm full professor at Université de Rennes in France, this university. So Luc, as I said to your jury members before, you have 45 minutes to present your work.
Okay, thank you.
There will be questions.
Okay, thanks for the kind introduction.
Sorry? We do not hear anything yet.
No, please start again. Sorry.
Yeah,
Okay.
peut-être que tu prends ça. Take the mic with you.
Is it better?
Much better.
Yeah.
Sorry for this.
No problem.
Okay, so as I said before, this work is about software system, and they are actually everywhere. They are providing numerous kind of services. And when you sit in front of your keyboard, you enter the digital world. And in the digital world, you earn the right to be a bit lazy. So it's a bit like being very rich in this physical world. You have a guy for everything. A guy to get rid of strangers, a guy to put your things into boxes, a guy to send messages to your friends and colleagues, and my favorite, to play music for you. So since the beginning of this research work in January 2020, our usage of the free services have increased a lot. And all these services have in common the fact that they are sending video in the network. And the role of this software system, X264, is to take this video and to compress the size, so to diminish a bit its size, so we are not overwhelming the network. And since human beings are different, there is some kind of variability between human beings and the usage of X264. So maybe you will want a fast encoding process, or your neighbor will want a high quality of video. But yet, X264 is made of code, and we are not experts or developers able to change this code. So to get rid of this problem, developers provide a way to encapsulate functionalities of the software system into software options. So without having to change the code, you can just activate and deactivate the option. And to make this explicit, they provide a documentation. So here is the documentation of the related code there. And they say what effect you should expect of this, from this option, maybe the different constraints, and how to activate this option with other options. So in practice, you just have to use the configuration. So this is the configuration. So I say I want to use X264. I say I want to activate KBAC by saying dash KBAC. I say I want to activate the motion estimator DIA. And I say that I want to take this video and to compress it. And for this configuration, the encoding process lasts 34 seconds. But when I change this configuration, when I switch KBAC to deactivated and the motion estimator to CISA, then I multiplied the encoding time by 4 or 5. So as a result, different software configurations lead to distinct performance values. And it wouldn't be a problem if we were not so efficient at building software options. So for X independent Boolean option having that can activate or deactivate, you have 2 to the power of X possible configuration accepted by your software system. So for small software system like grep designed to research for patterns in file system, you have a dozen of options and you have thousands of configurations. So it's quite easy to explore exhaustively the configuration space. But for medium-sized system like Gypster or Ph.D, you have more possible configuration accepted than the number of seconds in a typical human life. But it's quite difficult to roll all of this. And we can be proud of building really complex software system with thousands of options, but yet we cannot list all the different configurations. There are more possible configurations than the number of atoms in the universe. And the trend is to add options and not to get rid of options. So for this really complex software system, they have colossal configuration spaces. So for instance, when you compile a Linux kernel, you end up with a file of 20,000 lines, and each of these lines is activating, deactivating, or putting an option in a module. And your first challenge, besides knowing all of these options, it's to decide if to analyze whether your option tested will result in a low performance value or will add a lot of size in your kernel, for instance. But yet, even if you do that for all of these thousands of options, there exists some interaction. So, for instance, these 2 options can interact and change a bit the performance value. So, we argue that for this huge system, and maybe even for the medium-sized system, it's not humanly possible to predict the performance of configuration, to predict performance of configurable system. So state-of-the-art provides a solution, which is called sampling measuring learning. So with different steps. So first you have to consider a whole population of configuration, and you sample a few of them, as in the previous example, and you measure the performance of this sampled configuration. And we call the performance distribution the resulting performance values associated to this configuration. So you have configuration and performance value, and then your goal is to, it becomes a supervised regression problem. So you only have to learn a function linking the configuration value to the performance values. In the literature, they are called performance influence model, and they are a subset of the variability model defined out there. And you do that, so you train this function for a sample of configuration with the hope that it will generalize to the whole configuration space. So yet, state-of-the-art are proposing a solution to automatically predict the performance of configurable system. And this Ph.D, but there are problems, and this is the topic of this Ph.D. actually. So in the current practice of this performance model, we are just linking the configuration to the performance values. But there are more factors impacting performance. So for instance, the hardware platform on which the software system is executed. the operating system in which the software system is embedded, and also the input data processed by the software system. And all of this is impacting software performance also in a linear way. And we believe that it's not so easy to model these interactions. We think that these factors are actually impacting performance in a non-linear way, and that we should bring some smart solutions to handle this problem. So, what is a non-linear interaction? So here's a real-world example with X264. So first, let's consider two different setups. This laptop running this presentation and a small device, Raspberry Pi, running Debian. On these two setups, we run two different X264 configuration. One with backward block tree estimation activated, one without this option activated. And we do that on two different input data. Input video with an animation content, and input video with a vertical content. And for each of these combinations, we measure the duration of the loading process in seconds and the size of the resulting video in megabytes. So for instance, for the setup A, the configuration 1 and the input video animation, it leads to an encoding process of 6 seconds and a resulting video of 33 megabytes. Okay, what about this non-linear interaction? When you switch A1 animation to A2 animation, you're decreasing the resulting size of your compressed video or encoded video. While when you do that, you switch from A1 to A2 of the vertical video, you increase your performance. That's the type of interaction we are talking about. And yet, in this example, we exhaustively measure all the combination. But imagine you do not have all of this, and you have to interpret this. Which layer is responsible of this nonlinear change of performance? And also, only on this different layer, we only have two possibilities, but there is a combinatorial expression of the possible environments. So all of this together is the problem developed in this research work. And we propose this problem to the community. And we say that there exists a non-linear interaction between the different elements of this software system. So what's an element? Maybe on the hardware layer, the age of the processor, the number of core you have, if you are using a GPU or not. On the operating system, the version of your operating system, the options you activate or not, maybe the distribution. On the software layer, the way you compile your system, of course, the option, the anti-option activated, the version of it. And on the input data layer, it's more about videos, but you can guess for the rest. Maybe your size of your video, the length of your video, the resolution of it. And we are claiming that there exists complicated interaction between the different elements of this software environment. And we call it deep variability. And we believe that deep variability is impacting performance distribution up to the point that our performance models will not be applicable. If performance distribution vary with the software stack, all of this, performance model will be obsolete when we change the related environment. So why should you care? Who are the deep variability stakeholders? First, we are all users of configurable system. If there exists some interaction in the software environment, sorry, that's a live presentation. If there exists some interaction in your software environment, maybe your configuration will not be optimal. Your software configuration will not be optimal for your environment. If you are a developer, we see there is a combinatorial explosion of the number of environments. maybe it's very hard to document every possible environment and in general this interaction. If you're a researcher in performance, we are saying that performance models are not applicable. If you're a scientist in another domain, like biology, physics, and so on, you don't want this interaction to happen because it might introduce a bias in your experiment. Let's say you change your software environment and you relaunch your experiment. If the results are changing, you have to restart all for all the beginning from scratch, and you don't want that. And for companies, it's a bit like the reverse of users. Maybe your server configuration, so your software environment, is not adapted to the task you're executing in your data center. So it's a missed opportunity. Okay. So in terms of contribution, we present two contributions in this presentation. The first contribution is to characterize and spot empirical evidence of the existence of this deep variability. And the second one is to propose solutions to include this deep variability phenomenon in the current practice of performance models. So about the first contribution, we want to show the deep variability is real and to spot evidence of deep variability. And we are first presenting something on the input data layer, and then we will generalize at the end of this contribution. So about inputs, maybe we need to recall what's inputs because it's a very generic term. We say that inputs are workloads, a fixed workload processed by a software system. So for instance, a C file compiled by GCC, a JavaScript file interpreted by an engine like Node.js, an input video encoded by X264, or database queried by a database manager system like SQLite. And these inputs are different in terms of scale and complexity. It might be obvious for a lot of people, but you're not compiling an inner function the same way you are compiling the Linux kernel. And there are probably input-related optimization you can bring to the software system. And that's where it starts, actually. It's also the case for other software systems, like you're not dealing with database the same way according to their size, for instance. So in terms of performance, because it's we are there for that, to study performance, when we consider different configuration, we apply that on different input video for X264, it led to different performance distribution. So for instance, for the first video, the resulting performance values are like scattered, but for the second one, the performance values are aggregated. So if you're training a performance model on this video and you reapply this on this video, it won't work because it's not the same performance distribution. So that's what we address in the presented paper. Back to the measuring, sampling, learning process. So if you consider a software system, your goal is to try to link this configuration to the performance value with machine learning. And we are saying that inputs are interacting with configuration and changing the performance distribution. So this part investigates, demonstrates, and quantifies what effect configurable system inputs have on performance. As many other contributions of this thesis, it is an empirical work. So it starts by gathering measurements. So here's an example of a measurement process. So for this paper, we consider 8 different software systems coming from different domains. There's a compiler, there's a stat solver, there's a library to handle PDFs and so on. So with coming from different domains, but also processing different kinds of inputs. And the measurement process is the following. First, we select a configure system, we download and we compile a version of this system. And then we do two things in parallel. We search in the documentation input-related options, and we sample some configuration associated to this option. And we also select a bit set of inputs, often validated by the community. And what we do is we take all this configuration and we execute it on the inputs. And we measure as many performance properties as possible. So with all this data, we are ready to address different research questions. The first one being, do software performance stay consistent across inputs? And to study this question, we first introduce a metric, which is a Spearman rank-based correlation, which is an indicator showing the similarity between two different performance distributions. So a value of -1 is there if your performance distribution have reversed rankings. The value of 0 is there if your rankings between the two different performance distributions are not really related. And a value of 1 is there if your ranking are conserved between the different performance distributions. So in ideal world, we would have only Spearman rank-based correlation at 1, but we don't live in an ideal world. And we show on the graph on the left that there exists uncorrelated and negatively correlated performance distribution according to inputs. So what does it mean? It means that a configuration could be good for one input, but not for one another. And in terms of deep variability stakeholder, I'm a developer. I'm providing a default configuration, whatever the input. What I'm saying is that I will not be optimal for every user. So maybe I have to adapt this configuration according to the user. And it's also related to option. So do configuration option effects change with input data? And to study that, we consider two different indicators. The first, the importance of option. It's at 0 if the option is not important, at 1 if it's important. And also the effect of this option. So the effect of option is negative if by activating this option you decrease the performance. And conversely, if you activate this option and it has a positive impact, then you increase the performance. And what we are saying is that the individual impact of option change with input. And also, an option can be good to activate for one input, but bad for others. And in terms of deep variability stakeholders, we are targeting the researcher training performance models. In these performance models, the coefficients associated to the different options are fixed with the same sign and the same value. And we are basically saying that it should evolve according to inputs. So, okay. The first two different research questions are stating their interaction, but how much our performance evolving? Can we ignore the fact that the performance change with inputs? And for this research question, we consider two different scenarios, both predicting the optimal configuration for your configurable system, except that the first one is evaluating the difference of performance according to inputs, while the second one do not care about input sensitivity as well. So you're reusing the configuration. And we compare the performance loss according to these two scenarios. And the results show that when you prefer S2 over S1, you're losing about 40% of performance, 40 points of performance. And in some extreme case, performance can be up to multiplied to 10 when considering the inputs. So there is a real missed opportunity if you are not tackling this problem. So our researchers are tackling this problem. To answer that, we conducted a little literature review on 65 papers, all training performance models. And out of this literature review, we say that almost all the papers are concerned by this problem because they are including software system processing inputs as part of the protocol. But then, do they include a lot of inputs in their experiments? Only 2 over 3 papers are actually including multiple inputs. For the rest of them, their conclusion might not hold when we change the inputs, basically. So for 1 paper over 3. And also, they do not acknowledge this problem, or in the large sense. They are not even saying, half of them are not even saying that the performance should change with input, not even in a nonlinear way. And finally, we do a bit of prospection to say, is the paper, in the large sense, proposing a solution to generalize performance models across inputs? So just to have an idea of how state-of-the-art is tackling this problem. And finally, we want to propose some concrete indicators to estimate this input sensitivity phenomenon. So we propose a score based on the previous research question to estimate the level of input sensitivity. So let's say that tomorrow you are benchmarking another software system. Is your software system input sensitive or not? And if this score is close to 0, your software is not input sensitive, you can have 1 input, it's fine. If your score is equal to 1, then it's problematic, and you have to benchmark a lot to be sure to be tackling this problem. And besides, it's also the occasion to say, okay, we are showing the problem, but sometimes it's not input sensitive, and we can just kill the layer of input and to take a shortcut, actually. So it's not that bad all the time, just bad from some cases. Okay, what should we remind of this paper? Should be reminded about this paper that input sensitivity threatens the computation of performance models, and one performance model trained on 1 input will not be necessarily be reusable on any other inputs. And these results were also found by another team and published in the last year of ICSI. So in terms of deep variability modeling, we show an interaction between the input data and runtime option. So that's one work. But yet we don't have the time to discuss that, but we also published other paper. And the goal is to really show a modeling of deep variability. So for instance, in this paper, we show that the choice of software system, if 2 software systems are considering common set of options, their influence will change according to the choice of the software system. In this paper, we show there exists an interaction between the option chosen at compile time and the option compiled at runtime. In this paper, we show the version of the operating system is changing the impact or influence of options. And finally, in the last paper, we show that some parameter of the operating system can change the performance evolution of your software system. So it's a nice and friendly way to present it. So here is the non-digestible version. But why do we have this slide? It's because actually we want to gather and put together the concrete insight of our experiments. So if you want to have a summary of our work towards achieving this contribution, you just have this slide. And this slide also shows that we are not conducting some kind of dark magic. It's a research paper published in peer-reviewed conference or journals. And you can, if you disagree with this, you can read that and say we are not right. And yet we are not the only one to work on deep variability. There are other researchers working on this topic. So they probably don't know that they are working on deep variability, but we believe they do. So for instance, there is this paper showing as we have done, the interaction between input data and runtime option. But also this paper showing the influence of the version on the impact of runtime option. And this paper showing the impact on the hardware layer on the runtime options. And that's for the group, I would say, working in our community, but also in other, the second circle around our community. There are ongoing work that could be included in the modeling of this deep variability. Okay. So at this point, we have shown that deep variability is a real phenomenon that should be taken seriously. Now we want to push or to propose something more exploratory. So how to include this deep variability in performance models. And the goal is to train resilient performance model. I said that only considering the software layer is not enough, but maybe we want to embed this interaction between the different elements in performance models. And maybe the future of performance modeling is to build a performance model as general as possible and considering valid for as many possible software environments. So working for all the kind of hardware platform existing, all your choice of operating system, and there are quite a lot. All your variants of software, maybe compiled in different manners, including different runtime options, and processing different kind of input data. That's really a challenging thing. That's very ambitious. So since we are not Google, we are just focusing on the input data layer to present the result. And besides the sampling, measuring, learning approach, there exists also some kind of optimization of these approaches. Instead of just training a performance model on target input, maybe you can reuse what has been done and learned on a source input and use the similarity between the source and the target to reduce the measurement cost on the target. So, for instance, in the model shift approach, first you have to train the performance model on the source. Second, you have to learn the difference of performance distribution between the source and the target. And finally, you can combine these two models to shift your result on the source on the target. But transfer learning is better than standard way of learning. But you have to measure each time you add a new input. And yet we said that there is a combinatorial explosion of this possible environment, so there are plenty of inputs. And if you have to measure each time you have a new input, maybe it's not so smart after all. So for instance, let's say you're a user and you want to upload your video in YouTube. What we are seeing with the current practice is that you have to consider, let's say, 10 configurations. So you have to wait 30 minutes to have an optimal configuration. So I would say, okay, it's better than the standard way of learning. But as impatient user, I would say, what's the time to wait in 2023? I would completely choose this solution. So here I'm not, I don't want to say we don't have to learn. I just want to say we have to find a way to predict performance in a quick way. And we have to reduce this measurement cost. So how to do that? We propose to use contextual performance models. So to say, back to the dataset presented earlier about the inputs and so on, but to say we will add some domain knowledge about deep variability. We will compute input properties, so we browse the metadata of your inputs, and we say, for instance, if you have a video, I will I will store the quantitative value about the resolution, the content of your video, if your frames are complex, are disposed in a complex manner, etc. And add all of these input properties to the current dataset. And we show that for input videos, but for script, we can browse the AST. For that formula, we can count the number of clauses. So it's generalizable to all inputs. And then, back to the problem with the different videos, what we want to propose is just a really simple model taking both configuration and input properties and predicting the performance value of your software system with an unseen inputs. So we want to train machine learning models predicting the performance of software configuration, but also robust to the change of input data. And without to measure another thing. What we show earlier also is that this performance profile that we isolate are also stable in terms of domain. An expert could say, a priori, I will classify this input into this performance profile. And what we show is that the usage of these input properties allow to classify inputs a priori in this performance profile without having to measure anything. So it's the first step toward achieving a quick performance prediction. And then in terms of transfer learning, there have been some work showing that the choice of the source is actually a thing. We can use these input properties to select the best source according to a given target. And it's actually better than the random baseline. And it's close to what is achieved when measuring performance. But without taking new measurements, we are able to say what is the best or near optimal source input for your target input. Okay, so we have these input properties, they are useful. So we want to train these input-aware learning, input-aware performance models. So we've done that for the 8 different software systems in our paper. And we show that it's a proof of concept showing that it's actually possible to train a performance model valid for each input. And the more input sensitive your software system, the more difficult it is to learn a performance model in an input-aware manner. But also we show that the errors stop decreasing after considering 25 or 30 inputs as part of the performance prediction. So we are giving a complete insight. If you want to train an input-aware performance model, you have to consider at least 25 or 30 inputs, maybe more if your score of input sensitivity is high. Finally, we compare the different approaches. So we have a standard way of doing it, the transfer learning and input-aware learning. And we show that for a small budget of configuration of standard learning, the input-aware learning is actually outperforming it without taking any other measurements. So what we are trying to do is to generalize what has been done on many inputs And we are saying that if you do not know well your new inputs, we are able to do better for a small number of configuration trained in the training set. And also in terms of deep variability, because forgetting a bit about deep variability, generally speaking, when we apply transfer learning at some point, it's not beneficial to add other measurement on the target. When you have a lot of measurement on the target, it's not beneficial to add something coming from the source. And we are saying that thanks to domain knowledge about deep variability, we are able to enhance the current state of the art of transfer learning and outperforming the standard learning all the time. So, as conclusion, as messages, I would say we have to build quick performance models and to reduce the measurement cost. And input-aware learning is a way to encapsulating this deep variability thing by doing this quickly. And we show that with very low budget of configuration, we are even outperforming the standard way of learning your performance model. So it's time to conclude. What have we done in this work? First, we put a name on a problem. It's called deep variability. And we promoted it through different papers in conference venue. Also, it's mostly an empirical proof. We gathered a lot of data and proved that the phenomenon is real. I didn't talk about this a lot, but we provide also a way to benchmark deep variability with this usage of performance profiles. And finally, we discuss a practical implication of deep variability for researcher training performance or applying performance engineering in general. In terms of research practice, I want to promote also the fact that all this work is available. Please don't pay for this paper. We put the code and the data in the note on GitHub each time, and we embedded measurement processes in Docker. And it's available on Docker Hub. So just this slide. And we want to say that a lot of factors are actually concerned with this deep variability thing. In terms of perspectives, I want to propose two different perspectives. The first one, we show that we are able to train performance model in an input-aware manner, but that's not enough. And actually, we collected other work that I didn't detail here. For instance, we link the hardware properties to the hardware average performance value on the hardware layer. On the operating system, we computed some, and we built some kind of feature like the number of yes option activated, the number of no option activated in the Linux kernel linked to the operating system performance. On the software layer, we show that we are able to train a performance model both valid for compile time option and runtime option. And on the input data layer, we show that we are able to train a performance model that is valid for all inputs. So step by step, we are building the foundation on top of which we will be able to train a deep variability aware performance influence model. And each researcher in this community has its own way of seeing this deep variability aware performance model, I would say. And we want to promote this contextual performance model because it's a way to achieve this prediction in a quick way. And finally, my last message in this presentation will be we need to work together. Because a weakness in this work is we are only considering one layer at a time. Unlike other researchers browsing all the layers in each paper, but maybe we are going a bit deeper in this layer, but maybe that's not enough. And if we want to go deeper in each layer and consider all the layers, at some point we have to share the computational effort of doing it. So I want to promote the way that we have to agree on a common playground to test deep variability for all researchers in the Configurable system community. And maybe we can reproduce this success story paper. So this paper proposed something, a data set, that was reused a lot over the time. And yet this data set is not good enough for deep variability, but we can get inspired for this paper and work together towards benchmarking deep variability together. So thanks a lot for listening to me, and I'll be ready to welcome questions.
Thank you. Okay, so we will start the question round. So as usual, by the reviewers. So Lydia, do you want to start the questions?
Yes, of course. Can you hear me?
Yes,
Yeah.
perfectly. Well.
Okay, because I changed the auriculars. Okay. First, I want to thanks for the invitation to be part of this jury. I'm very glad to be part of to be with my colleagues and also to have the opportunity to read this very interesting thesis on. Thank you. Well, I would like to be there, but couldn't be. Congratulations for the supervisors and for Luc, for the PhD student, because he had done a very good work. I know he had to make a lot of experiments and analyze these experiments, the output of the experiments, and repeated experiments, I suppose, thousands of times, and study all these statistics indicators and so on. So this is a very complete work, and I appreciate and I congratulate you for this. This first, okay. Having said this, well, in Spain we don't have a limit for talking. So I'm going to start, and if you consider I speak too much, please stop. Okay. My first question is, well, when I have read this dissertation, I say, well, I will find the output will be a set of algorithms, a methodology, or a tool or something. But finally, I said, no, I think that's only the experiments there, and it's good, but I would like that you clarify me that what are the deliverables of your thesis?
Yeah, so that's true. We didn't provide a way or many tools. I would argue that there are Docker containers that can be used to, for instance, benchmark a configurable system, for instance, and that the code is there, but there is no big library benchmarking deep variability. That's true. That's actually something we could have done. But for every paper, we try to be as general as possible, and we try to provide ways to add something. For instance, in the SPLC 2021, we provide a way to add your own software system with compile time and runtime option. So we are not proposing a general way or general tool for everything, but step by step we are proposing something, and we try to be as general as possible when designing this tool. But it's true that it's not an industrial process right now.
Yeah, this is good. I mean, to define our process or our ecosystem of algorithms, tools, or something, because if I want to reuse your knowledge or what you have done, for me and for the community, it's difficult. This is why I think it's as a future work, of course, it would be nice that you work on providing something more concrete, so the rest of the community can learn and use it. Well, this
Okay, yes, the SPL Conqueror version of deep variability, like something like this. Okay, yeah. Okay, yeah, it's a lot of engineering, but it's true. It should be something to achieve. Yeah.
Okay, well, as a general comment, I'm very happy that finally the community start to consider hardware, well, what you call layers, this hardware, input data, software, as part of the analysis of the variability. Because in last years, my group and perhaps Rick and very few of us try to propose this kind of things, try to say the same things that you are saying now, but perhaps without telling them the variability. And sometimes we, we were the only ones. So I'm happy, really, I'm very happy. But my question here is that, well, you say that hardware, of course, the features that are related to hardware are strongly influence the performance of variability model. But if you, what I don't get it is that, the hardware is there, some parameters during compilation, for example, are there and are relevant, and input data is there and is relevant, but you also have the variability model. So do you propose, or what do you think about how we can model all these like contextual features or related to this variability model? I mean, you have these layers, but these layers are not a formal model, okay? And they are not connected in any way to the variability model. But sometimes in variability model, we find some features that are hardware features, you classify them. I have, for example, in my some of the works or the thesis I'm supervised, I put separated different models, one for hardware, another for software, but these multi-layer models are interrelated. But what I don't see here is that where are these features? Do you understand my question, or?
So I get two questions in your speech. Just tell me if I'm wrong.
Yeah.
So first one is how to activate this kind of features, and maybe a question is about also how to interpret the different effects of this feature. Am I correct?
No.
Okay.
Sorry. I read.
That's
No.
fine.
Okay. My first question is, how do you model this software and hardware feature as part of the variability model? You can answer me in any way, or simply I know this is relevant and I put it in the performance model. But from my point of view, to model this explicitly is important. So this is the discussion.
Okay, so we consider them as part of a feature of this performance model. It's only a quantitative value, exactly like configuration options value that is processed by as part of this table. So we concatenate in a way this feature values to the configuration value, and then it's the model is supposed to establish pattern of interaction inside the model. So just we have a table of environmental properties and a table of configuration, and then the model is taking both, but as one big table, I would say, and is doing the rest alone. But there are also ways to do that with causalities and to explicitly say I want to build a graph, a directed acyclic graph with the different elements, but we are not proposing this PhD. We are just saying it's one big table with features.
Yes, and this is a big challenge in the community because you have done what everybody that works on performance model they do. They forget about the variability model. The tree is no longer there in any way,
Yeah.
and you have tables that are very easy to process. Okay, but
Yeah, but I think maybe a recent work has been published in Eurosys 2022, and they are proposing a causal performance model. So exactly like you were saying, taking this feature and trying to establish the causality between these different features. So there is another proposition of, I would say, formatting of these features. And it's
as part of the variability model, or in different variability models, or in I didn't understand.
in causal performance models. So it's a graph with the different elements.
Natural,
A bit
in
like
a different notation. Okay.
yes, but it's a bit like this actually with arrows, but except it's actionable and only valid for one environment.
Okay,
bit
because
like,
yeah. Yes, I mean, and it's good that you compare with the related work that many groups are doing in this direction, trying to express all this contextual information that strongly influence the performance of a variability model, of systems, of configurations, as part of the in different models, or at least connected to the variability model in some way. Okay, good. Another thing, well, you have made a lot of experiments. Many experiments, use cases, and you change the use cases. The use cases are for different domains and different parameters, blah blah blah. But when you you choose a certain performance indicator, you have chosen the typicals, the classical, meaning the time for compilation, the execution time, size of the bytecode, and the typical. That I understand. You have done a very great work, because the experiment takes a lot of time. My question is that, well, these are special performance indicators, but you really didn't made the experiment using very different kind of performance indicators, because you have other performance indicators, like, for example, energy consumption. That's a very peculiar performance indicator. And especially, it's very hard to make experiments trying to calculate the energy consumption or the energy footprint of certain configurations. So, do you really think that all your findings can be generalized to any kind of performance indicator, including energy consumption, security, and others? There are many.
Mm-hmm.
What do you think?
Yes, I think, for instance, it's maybe a bit little in this slide, but I think we measured lots of the time, but we also measured some kind of number of operations per second, number of conflict. For instance, for the size of the encoding video, the time of the encoding video, the CPU usage, the number of FPS, the FPS, the bitrate. So we are not only considering performance 2 or 3 performance properties, we brought a bit larger. And about energy consumption, we did not do it. We planned to do it, but we didn't. It's because it was an additional engineering issue, and I can know for sure if it will, if the result will be propagated to energy consumption. But I guess that in some research work, the CPU usage is a bit correlated to the energy consumption somehow. So we have indicators not directly related to energy consumption, but correlated with it. So I don't know if I'm confident, but I will be surprised if our result propagate to such indicators.
Well, the energy consumption is very, very special performance indicator. So I'm not sure that that your findings can be, generalized to also to any kind of performance indicator. I'm not sure. I don't know. I cannot tell you. I guess you cannot generalize your result to other performance indicator, but I think that more experiment. You have to perform to make more experiments to conclude this. For the moment, these performance indicators are good, are valid for many, systems or developers that are interested in these performance indicators. But I think that more work should be done, more experiment before concluding that any type of performance indicators behave like you can apply the same findings. Regarding yes, tell me. Yeah, you can speak.
No, I agree with you. I can say before measuring. I can tell my opinion based on what I've been doing, but I agree we cannot conclude about other indicators not measured in these stages. Yeah.
Yes. Also, you have identified these layers that are the ones that really influence or can influence the performance model. But I suppose that you are not sure that you have considered all the possibilities. For example, one thing that in this community people always forget is about communication. Okay, for example, if you want to calculate or the energy consumption or the latency of a distributed system that is connected or through Wi-Fi or any communication protocol, for example, the distance between the device and the access point is relevant there. Okay, and it's something that affects several, not only one, several performance indicators. And I think that it's interesting to include also the communication, especially nowadays that all the systems or the majority of them are distributed. Consider, the cyber physical system, Internet of Things system. I think that communication should be considered more or should be explicitly modeled and considered during when you make this performance model. So this is a suggestion also. It's something that I try to do all the time, but I think that the only one, I don't know.
Yeah, so this is a simplistic representation of what is deep variability. We are forgetting a lot of things. Obviously, there is not only 3 different elements per year. It's not only it's a way to present it, but maybe I don't know if if your laptop is in battery saving mode, your performance will change. As you said, with the network constraints, there are lots of problems going on and stopping down your process, so enlarging the time, for instance. There are plenty of other options. I'm not attached to this specific slide. It's just what is behind and the modeling of the different constraints between the elements that matters. And like you said, maybe there is, for instance, if your software is in a container somewhere here, maybe your choice of programming of the developer here. We can add other layers and we can add other elements. And I agree, the networking is one of them, the network constraints.
Okay, yes, and also, for example, when you say operating system and software, perhaps, or the virtualization that now, is the tendency because people are developing this application by connecting different services or microservices, and all these services are containerized. So also it's important for the future, of course, to consider this kind of features. Okay, what's more? I think, well, you have applied several performance models. You have used regression trees, etc., etc. How do you calculate, or have you calculated exactly the error that you are making when you predict, or yes, you predict some value, some corresponding to a certain configuration? This because depending on the error, perhaps for a certain developer, an error that I don't know, 20% is acceptable, but for other domain they are more strict, and this error rate should be the minimum one. So how do you calculate?
So what would be the consequence of an error, a given amount of error for the developer and for every actor? That's what you're asking?
Sorry, I didn't understood.
So you want to know
yes,
whether
you have a configuration. With your machine learning algorithm, you predict a certain value because you didn't measure, so you predicted. But when you predict, you make an error because you don't know what is the exact value. What I'm asking is, for a certain system or domain or developer or enterprise, I don't know, a certain error is acceptable, 20%, 30%, or I don't care so much, but others can be more strict. And I'm asking simply, how do you consider this when you made all these experiments, the error that you make?
We cannot guess for sure how the different actors and the different system will consider our results. I don't know the level of the requirements of developers to ensure. It depends on the team, it depends on many factors. So I cannot know. We explore, we didn't, one thing missing, maybe to answer your question, is a study for two developers and to present the results. But we try to reach developers, and it's not that easy. We are mostly getting their way by browsing the commits of the history of GitHub for a given software system, but we don't know for sure how they will react to a performance model making 10% of error. We don't know for sure. But if we are, generally speaking, we are making like 5 or 10% of error, so I guess it's acceptable, but I'm not in the head of a developer.
I think because when you train your performance model, if you are using supervised learning, you have to stop in a certain moment to say, or I guess you simply say, well, the typical that in machine learning area they use the 30%, you have to train the model with a 30% of in this case configurations. Is this or is simply you have trained with the amount of
in terms of splitting the training set and the test set, or
yes,
I don't know.
In the training set the idea is
it
that
depends.
the greater is the training set, you reduce the error rate. But sometimes you have to sometimes this is not true, because with if the training set is not so big, so large, you can predict the performance value, and you don't need to include more configuration in your learning set. Is what I'm trying to say, is that if you have applied certain heuristics or something, or you simply say, well, I training this for this use case, the 30% of the global configuration space, I train this. I don't using uniform random sampling, I suppose, or something like this. And
yeah, I see your point. So how many configurations should we include in the training set? To ensure a certain performance, certain model error or something. Well, again, I'm sorry to always answer that, but it depends. It depends on the complexity of the configuration space. It depends how many options you choose. For instance, we conducted some experiments, some performance model on Linux, and we have so many options and so many interactions between these options that you have to consider lots of configuration, like thousands of configuration. But for x264, we reduce that to a subset of 20 options. There are not so many interactions, so we can have like hundreds of configuration, and it's already enough to have a 5% accuracy error, 5% error, sorry. So it depends, and I would say for medium-sized software systems that are pregnant, and overall the one we are targeting, hundreds of configuration are enough to train a decent performance model.
Okay.
If you don't mind, I will try to leave some questions to the other members of the jury.
Okay. I only have one last question.
A last one then.
No, my last question is, the work of Norbert Simon and all this group. You have recommended some performance models and sampling method, but the conclusion are not exactly the same as the other. And I think that they are, I don't know if we can really recommend a certain kind of performance model, meaning the regression tree or the CARP is the best one, because none of them is really better than the other options. So what do your opinion about this, simply?
Okay, so there is plenty of performance model out there. Of course, we have our own choices, and we all converge in terms of machine learning algorithm. I think we all consider gradient boosting regressor, for instance. So in terms of approaches, we are having different choices, of course, because we are promoting our approach, and it's a competitive field, so that's life happens. But we have some convergence towards some small points, and I would guess that every approach is working in its way. You just have to find the right use case to use it. And for instance, if you want to interpret something and you have some kind of interpretability, performance influence models with, as proposed as Sigmund and colleagues, are typically the kind of thing you want to use, because they are providing a way to show the interaction between the different options. And even if it's not our approach, it's something really useful. So does that answer your question? Or?
Yes. Thank you. And congratulations again for your hard work, and I wish you all the best. Thank you.
Thanks.
Thank you, Lydia. So, Rick, Abizer, if you want to continue with the questions.
Yeah, thanks a lot. And yeah, I also want to thank Luc for this very interesting presentation, and also I want to thank Lydia for asking many of the questions. But I still have a few left, but don't worry. So first, a question that was one of the first questions that came to my mind when reading your thesis. You always talk about hardware and software and operating system layers and benchmarking, but what about virtualization, containerization, as you have it these days quite a lot, I would say, in modern cloud infrastructures, cloud-based software? What would this mean for your concept of deep variability when really applying this in a cloud-native environment?
It would add more layers, and it will bring, of course, other factors that fill the gap between our simplistic way of representing it and the concrete reality of developers with different interactions. Of course, you have a Docker container, some bandwidth constraints. Maybe at some point you lose your network connection, everything collapses, then it goes back. So of course there are other constraints to add when adding these containers and these virtualization layers. And maybe when you virtualize also, you have different choices inside your container, different libraries used. So in a way, maybe more than one layer is impacted by the virtualization part. So I would say not only adding a layer, so my first answer was this, but adding a constraint, other constraint between the layer and making it really more complex.
But wouldn't it also, I mean, in an extreme case, mean that performance to some degree becomes a non-issue? Because in the end, the scalability that these infrastructures provide doesn't matter that much what your performance is anymore. So wouldn't it shift the focus more to other non-functional attributes a little bit? So in terms of understanding the effects of the configuration choice on, I don't know, on certain libraries, as you said, or something like that.
So yes, there is a risk also that it's changing the existing interaction. So we are showing some interaction. Maybe when you virtualize your software system inside this container and so on, it's changing the interaction. It would be quite bad actually, because all these conclusions will fall. It has to be tested and measured, but it is likely to happen. But yet the global model and the global problem will remain the same, even if the interactions are different.
I mean, the really cool thing I could imagine is that if you train a performance model for a certain container environment, and you can more easily guarantee that the configuration stays, so the hardware configuration stays the same on a virtual level, right? But you just don't know what happens under the layer, and that you are allowed to see in the actual cloud infrastructure. So that's what I was basically arguing.
So when you virtualize, you can see that as a new environment, and maybe you can apply some kind of transfer again. It's maybe a naive way to see that, but if it's changing, maybe we can transfer what has been done before. Maybe some interaction will hold, some will not, and you can apply this. But still, we're hoping that some interaction will remain the same, whatever the virtualization layer, whatever the hardware resources allocated to this container, and maybe, hopefully, there are some factors are quite stable and will remain the same.
Would be quite an interesting avenue for future work, I would say, yes.
Yeah.
So maybe a little bit of a different question in terms of related work. You put quite some focus on papers that predict performance in the context of configurable system, which makes perfect sense in the context of your thesis. But in terms of representing deep variability, or basically representing variability on multiple layers, there has been quite some work in the variability community also in early days on multi-view, multi-level variability modeling, so where you can basically distinguish different layers already. Did you have a look into such works, and how could maybe those be of help?
So how to format deep variability, or with respect to the related work?
How to basically represent or model deep variability using existing.
Okay, so I think in almost 2020 there was a proposition to propose some kind of annotated variability models that we could use maybe to enhance with the whole environment to model this kind of deep variability. And yet I do not know exactly the right format to do it. Maybe you had some paper in mind when you were asking this question. I don't have any fixed opinion about how should we model this apart of taking the causality into account. And
I'm sure it will be hard to directly use anything, but you can definitely, I think, build on some of the works to do that. Okay, so
yeah, but maybe a feature model is not enough, I would say.
Definitely. So I've seen works, for instance, in the area of systems where they had different types of variability models for software, hardware, electronic, mechatronics perspectives, and allowed to model constraints across these models. There's work even going back to 2006 by people from, I think, Berlin, doing something on multi-level feature models, but as we said, feature models will not be enough. So what we will need is a way to integrate different types of models that are capable of representing non-functional properties and attributes and things like that.
And the ideal would be also to have these models that are actionable variability models. Not only, okay, there is a model to show the interaction and so on, but how to include that as part of performance modeling. Maybe that's why the focus of this PhD was not in this direction, because there exist plenty of people capable of modeling the deep variability in way different manners, but including this model into some machine learning algorithm is not something that is trivial. At least that's, I think so.
That I definitely agree. So it's coming to a different question. I think on slide 17 or some around that, you and motivating that the key factor are the inputs. And I saw that the key factor for your slide are the inputs, right? Was that the right slide? Let me see. No, it was not.
Because you were talking about input properties, so I switched.
Yes. So you said software systems process inputs, right?
Yeah.
And it's always file, a video, a database, and the system processes that. What I immediately thought was, but what about an interactive system where a user interacts a lot with the system, and the system does something, and the user reacts, and the system does something, which you cannot easily benchmark, right? Because you need an actual user to sit in front of that, and that's also something that how would you then train a model based on user input? How would you do the benchmarking? So how would an interactive system change an effect on the results?
So not a fixed input, but some way around between the user and how the user can use different steps to provide inputs to the software system, how it will generalize to that. I guess we have to add a temporal dimension to the different inputs processed by the the software system. If you are sending some text and waiting for the feedback of the software to add another sentence, for instance, maybe we had to provide a way to encapsulate this history with a conversation with the software system and to add it as part of the model. So maybe we have to switch from just the space version of the performance model to a space-time version of this performance model. And actually, I don't know. I think I didn't read anything, at least in the configurable system, taking this into account. But it could be just a variable with yes, a temporal feature with the different with the order of arrival of your different input parts, and it would work. But yeah,
I mean, there is some work on temporal feature models and on variability in space and time and how to make this happen. So from a variability perspective, I'm sure this is doable, but from a performance model and machine learning perspective, this is quite a different story, I think. Then when I read the third part of your thesis and what you presented also today, I think you undersold, so to say, a little bit your contribution, because in the end, it's not only about extending the lifespan of such performance models, so to keep them alive, but it's more, I think, about increasing the usefulness, right? Because in the end, the user needs to be right?
yes.
So what my question is, how would you investigate this in a user study? How could you actually incorporate feedback of users on the usefulness of these models?
Okay.
You mean to have unlimited resources and time for another PhD? So
Yeah.
Yeah,
of course. So how to include the user feedback on this performance model? So besides having just a feedback loop, retraining the model and doing a full retraining or light retraining, because it's too easy, I get for a solution. So include feedback of users in performance models. Honestly, I don't have the answer right now.
I mean, I know that for machine learning, there is some ways to do that, and this can be done with the actual virtual user, but yeah, this is maybe a whole different story. What I'm also wondering a bit, staying with the user perspective here, so how would someone who wants to build on your research, right? How would he or she start? So what would be the first thing you would suggest someone does? Look at the data and make sense of it, or is there what of the material and especially the data sets that you are providing online would be the entrance point? What would it be?
So before, okay, so thanks for the question. Also, before starting everything, a new PhD on this, maybe we have to agree on this benchmark and to establish a common benchmark on to test and browse the environment, to test the variability. That would be the first step, because otherwise this new PhD would have the same weakness of my thesis. It would like, okay, you have lots of data sets, but no one can reuse that and can, of course, we provide the data set, but I don't know if it's so easy to build on top of that. So the first step is to benchmark the variability, provide some common benchmark, and then based on that, try to add more and more layers, and to say, okay, I take the input aware part, and I had another layer with by adding incrementally a compile time option, and then I made vary this operating system, and I had this on top of this performance model. So maybe I would suggest to do that in an incremental manner, but after defining what system should be included as part of this benchmark, what layers, what kind of environment, so we can all check and verify the results.
Okay. So maybe one last question before I hand over. Talking about a common benchmark, do you really think we will have to have one common benchmark, or would it more make sense to like have a set of benchmarks the community can agree on? Because I think it's really hard to come up with one and agree.
Maybe one benchmark is not enough, but at least a standard way to put your benchmark in a data lake and to make them usable with the same format, same formatting, the same way of expressing the data. So you can build your performance model for. When I say one dataset, it's more like one unique way of benchmarking the variability. And maybe more than one dataset, we have to agree on a way to test and benchmark the variability. And also there are engineering constraints like where to put the data, the framework have to be designed, and we have to all agree on that. So it's a whole process, I would say.
I agree. Okay, thank you very much. I yield. So whoever says.
Thank you very much. So Puyan, Jamshidi, do you want to continue with the question?
Sorry. Can you hear me?
Yes, there is a little echo though. Can you speak again?
Let me fix the echo. Just give me a second. So I think
Now it's better already.
Yeah, it's better.
I hope it's better now.
Yeah.
Thanks for the great presentation. I really enjoyed the presentation and the comprehensiveness of your work. So I start with one question, clarification question related to building this new way of performance model, which also capture the variability in the input space. As I understood, you group the inputs. Could you elaborate on that a bit more? Because the example that you provided was related to X286, which is, we have some solid grouping, but in general, for any configurable systems, because we have some variability, like we might have it discrete inputs, or we could have some temporal inputs. How would you, analyze your approach to these different type of systems?
Okay, so how to group inputs, maybe with different nature of inputs, both for with temporal complexity and maybe spatial complexity also. So the goal would be the first step. So maybe it's a two-step process. The first step is to measure some inputs and of your new software system, and to do a bit of clustering as we did before. So to say maybe it's not worth it to do this clustering if your software system is sensitive. But the first step would be to gather together the group of inputs having the same performance profile. Maybe it's three-step process, sorry. The second step would be to analyze this performance profile in terms of domain, to say, I understand that this input is processed this way because of this element of the code. And finally, once you have the domain knowledge about these inputs, you can browse the input properties, and it's even for temporal inputs and inputs having different natures, you can compute these quantitative values and try to classify the inputs into performance profile based on these values. And it's always possible, whatever the nature of inputs, to compute these input properties. And the nature of inputs is not really changing that. So is that
so essentially at this stage you still need additional performance measurements, right? But your claim is that for this type of profiling, you don't need to consider the variability space in the configuration. You can do that independent on the configuration of the system. You can like do this profiling with the default configuration of the system. Is that correct?
Yes, it's hidden. The configuration part is hidden in this profile because you're computing it by providing a configuration, but it's hidden. You compare the different performance distributions there, and we are not forgetting the configuration part. We are just abstracting it to make this graph and to establish these profiles.
I see. Thank you. One other question I have, like from your empirical side of work, have you like discovered what was the key underlying reason or the cause of this interaction between input and the rest of the configuration space the software kernel part? Did you like look at also the code to understand what actually caused this deep variability in the space? I do agree it's a very insightful. And by the way, I really enjoyed reading your work over the time in the past few years. It was excellent. SolidWorks, I do enjoy it. Thanks.
Thanks. Sometimes it's really simple. And in this slide, for instance, when we try to understand the reason why are inputs and configuration interacting, so there we are targeting Poplar. That's a PDF library. What we are doing, we are saying, I take my PDF, I extract the images, and I put it somewhere else. And this performance profile, the first one, is composed of presentation with many images. So that's teaching courses or photos embedded in a PDF and so on. The second file is just text PDF. So you don't have to do anything. So it could be as simple as that. Your performance profile is not correlated because you don't have the same content of PDF. And sometimes it's like for X264, it's a bit different. Like in your first groups, you have only action video, and in your second group, you have not action video, so not something with a strong temporal complexity, but you have a big resolution video, and you have parameters of X264 specifically working well for these big settings, but when you activate it, it's not working well for the action video. So we're not looking really at the low code, at the code level, at the low level. Other works have been doing it, Stefan Mühlbauer and colleagues. But we are trying to understand which configuration option is interacting with which input, and also can present something about the knowledge of developers. So back to the X264 case, we brought the history and the commit of X264 from the beginning of the launch timestamp of the software to the recent one, and we also search for input sensitivity knowledge, and we show that developers are aware of the reason why the performance is changing across inputs, and sometimes they include that as part of commit messages. So a way to get this knowledge is also to analyze this commit and to search for this reason. Maybe we can include this reason when trying to highlight these performance profiles.
Thanks. Possibly the last question. I would like to ask whether you had any direct interaction with the developers, or have you encountered any particular use of this all beautiful performance model that we in academia build, whether they use any of these in practice? Because you have done and you have looked at least the commit messages in GitHub, but I was wondering whether you had some interaction with developers to see whether, like, any type of, whether ML-based type of models or other type of models that we build in academia, whether they use any of those in practice?
I'm afraid not, at least from my understanding of it. We try to contact and to reach developers. For instance, we sent a dedicated presentation presenting our result on input sensitivity to X264 developer, but they didn't react. We were not expecting a lot, but they didn't react exactly to the results. They were more concerned about some other details on our usage of X264, and we were not up to the point that we could talk of performance models with them. It was a bit far from their concerns, I guess, and at least for the developers. For other developers, for X264 developers, they were not using it. But other software, for other systems like MongoDB, you have, like in the ICP community, for instance, David Daly, who is making lots of performance modeling on MongoDB with the computation of change points, and is really in advance compared to other software systems, and we take part of this data challenge part. So we did not interact a lot, but we know for sure that they are using machine learning models to try to detect some bug and detect some change points related to the different environments considered for MongoDB. So at least there is a part of developers that are actually using something similar to performance models. Maybe not ours directly, but maybe we'll go there in the future. We also have to show the benefits of our work so they can use it after.
And do you see any like, do you suggest any approach if in academia we should, like, for example, PhD student who continue your work, should follow in order to make that happen? Because this is a very big concern that I also feel that, we do research and we publish work, but nobody uses this in practice. So I feel really uncomfortable continuing doing this line of research if in practice nobody uses them.
Yeah, exactly. Maybe a way to process is that it's you have to be careful because some developers can react in a bad way, I guess. For instance, in the case of the Linux kernel, but you can propose some modification of the code and maybe a way to test performance and send them the results and see. But in an automated way, I would say, don't waste your time trying to reach them. Do that in an automatic manner and browse large developers in a large way. So you don't lose your time doing 50 different presentations for 60 different software systems. And a way also to bring something to these developers is to show them that we are able to find a performance bug there and just to launch some issue on their software system. That I think that's something a way to include ourselves as part of their concrete life, concrete work, and that's maybe how we should proceed to go in their life and to be included as part of the design process of a software system and to step by step bring performance models into their life.
Thank you. Thanks again for this work. Awesome.
Thank you.
Thank you. So Maxime, if you want to take over the questions.
With pleasure. So first I would like to join my colleague and congratulate you for this very dense and interesting piece of work. The more we go into defense, the fewer questions we have. So I think I will have only 3 or 4. Especially my first one actually bounces back on Puyan's last. So I will start over with this story of introducing your method into the industry practice, as we could call it. So, I mean, the way software is currently tested from a performance perspective is drastically different from using performance models, as you know. So they do scale testing, stress testings, things like that. And I think that actually, as you said, if you try to reach them out and propose an entirely new thing, they will just reject the idea, probably because they want to keep their habit. So what if we started actually from their perspective and their practice? So I guess you have some idea on how software engineers do performance testing today. I'm not talking about variability here, only traditional performance testing. So now if we wanted to introduce a methodology based on performance model, how would you enter the debate with them?
Okay. So how to improve their way of testing performance of software system? That's okay.
Yeah, not only improving, but rather adapting their way, so still keeping their way, but trying to gently introduce the notion of performance modeling. How would you see that?
So maybe we have to make them understand the complexity of. So it's a hard question, I think. We have to make them understand where they are not good at with the current way of testing software systems. And we have to show exactly as nonlinear interaction there. We have to show this, but in an automatic mainner and to show every point of variation causing a difference in the way they test the performance of software system. And maybe at some point, if there are many interactions like this, they will say, okay, but I cannot deal with that manually. So I have to have a way to embed all of this. And then we can propose a model and to say, okay, you don't have to do it manually. Here's the performance model encapsulating these different interactions. But it could be a way, but it's more a human problem than a technical problem.
Yeah, that definitely is. Yeah. Just to clarify, I did not expect an exact answer. I just wanted to have your opinion because, as you said, this is really a challenging question. Perhaps related to that, for example, I remember that in the chapter of your thesis where you speak about grouping inputs based on their performance profile, something that came to me is that this is actually very much different from the way developers group their input, because developers generally try to group inputs based on what you could call the input structure. So at the static information that allows developers to put inputs into classes. So you kind of with your approach, you kind of bring a new way to observe the space of inputs, and that this is drastically different from the view that developers usually have. So again, what is your take on this, and how do you feel we could perhaps explain this new view to the developers, or at least try to reunite their views with yours?
Okay, so yeah, there is two different ways of establishing this performance profile. You're right. There is a new way, an automatic way, but it's maybe I'm not talking about the. It's not so obvious to have this performance profiles in an automatic way. There are many choices for it. Maybe it's a bit technical as answer, but I will switch to the human part later. But there are some linkage function really changing in your clustering parts, really changing the final profiles. So in the end, we try to analyze that as developer did, and to find profiles that are actually understandable in terms of domain. So we have to adapt to the way of proceeding of developers, and it's not so automatic on our way. It's automatic in the way that we are able to take some profiles, but there are different ways of establishing these profiles. And finally, we can propose the way that is closest to their way of with domain knowledge and the different ways of separating inputs. We have to propose them the way the closest to their habits, and that's how we proceed.
Mm-hmm. But for example, have you observed that, for instance, you could have inputs that are very similar in structure, but have drastically different performance profile, or vice versa? Have you observed this on some examples?
Yes, I don't think I have a slide for this, but typically for X264 we have lots of videos, and sometimes you have very close content of video, but in terms of encoding, there are some specificities in terms of colors between your videos that is not perceptible for us humans. But the algorithm, we say, okay, in terms of configuration, it's interacting in some strange way because you have to compress the block, and there are fancy things happening in the video encoder that we don't get as human. So sometimes it's tricky, and even for developers, because they say, okay, it's two animation movies, so okay, let's take one of them and include that as part of the test profile. But it's yeah, maybe we have to show the drawback of this random selection of benchmark of inputs.
Actually, I actually think this is a very nice example that you have given there, because clearly it goes counterintuitively with the developer typical mindset, but still you can show the importance of considering performance. Great, thanks for this answer. Now my next question would actually relate to one of Lydia's first comments on the fact that you have a lot of results basically, but yeah, as a scientist who like to extract a general methodology out of that. So I think you have this methodology in mind. I mean, we have attacked you a bit on this, but that has made me think about a completely different domain, which is medical imaging, which is a domain where deep learning is being increasingly applied for tumor detection, medical diagnosis in general. And the difficulty actually is that let's say the experimental settings in which you do medical imaging have a lot of variability, because if you do chest X-ray of different population in the world, for example, or on different machines, or simply in different clinical condition in general, it's really hard to have a model that was tailored for a specific set of clinical conditions and then applying it in another country or for another population. So I was wondering if we could apply the same methodology that you have proposed for performance prediction for configurable system to the domain of medical imaging or similar domains. And what would be let's say the very generic methodology you could propose? What would be the first steps?
Okay, so the first step was, would be an analysis of the difference to say there are, in terms of biological neuroimaging, these two clinics are really different. So maybe the first step would be to understand the difference between the clinics, and again to do some kind of profile of clinics and a way and to establish some kind of similarity between the different environments. So again, it's the same thing with inputs, but with the physical environment, I would say of the clinic. And then we can apply transfer learning from a set of neuroimage of this experiment to the other one. But maybe as a scientist, they will be more likely to do some sort of calibration at first, and saying we want to tame the difference between the different environments, and after cleaning the difference, we have this common playground on which we can apply this phenomenon. So I will adapt my models to kill the specificity, to understand the analysis between the different environments, kill the specificity, and then apply a general model for each, and then reapply the specificity when my model is working for this. But finally, for medical people, I think it should be a calibration phase when starting with measurements and saying, okay, I already observed something like this, so you are diverging from this amount compared to the average and so on.
Okay, I see. Thanks for your view. Now I have a very detailed technical questions closer to the subject. So I remember that on some occasion you have used some basic sampling algorithms. You mentioned uniform or completely random sampling. So you probably know that, at least your supervisor knows this, that sampling in variability is a topic as a whole. I mean, we try to do efficient sampling and effective sampling of configuration space using uniform sampling or some diversity-based sampling. So do you think that there would be any benefit for your approaches that you have developed in your thesis if you had used or investigated, could say, smarter ways of sampling.
Actually, yes, very good question. So maybe we can use burst in the future. And then it's not published yet, but we have shown in the context of compile time variability that there are smarter way to sample. So it's very, again, it's technical. So for some compile time options and some runtime options, you only have an interaction between this if you have a specific input. And if you do so, the way you sample your configuration, when training a performance model, understanding the interaction between compile time option and runtime option, you may say, I don't want to measure too much. So there's a really a difference in terms of strategy or sampling strategy, the difference of cost and taking the cost into account when sampling is something that makes your performance model working on compile time and runtime level is more efficient. Like we can almost gain half of the measurement cost at some point.
Okay, so if I got it right, the idea is to not only take into account, let's say, the features themselves, but also their impact on performance in order to get a sample with the lowest cost as possible.
Yeah, to locate the interaction in the configuration, and then to adapt the sampling strategy according to it.
Okay, interesting. And then perhaps a very last question, which is a simple one, I would say, or perhaps not. What was the most surprising findings that you got?
The most shocking one, I think, but it was because it was really a real case. It was on the MongoDB scenario. The fact that you change the thread level and the same code, according to the user environment, will cause a drop of performance in some case and an increase of performance for another user. And that's not the biggest, fancy, sophisticated interaction we got, but that's something real. And as a developer, I would say, okay, how do I deal with that? I spent like 1 week to change my code to bring this optimization. And yet for some user, it's some users are satisfied, but I destroy the life of other users. So what should I do with that? And when I try to make myself in the position of this developer, I say, okay, this is shocking. And this is actually what I would say shocked me the most when doing with variability. Okay, it has concrete impact on developers. More maybe than the sophisticated way of sophisticated interaction involving 3 or 4 layers. Okay, that's good, but that's a technical shock only. So it's more the human shock. That's
I see. Interesting. Thank you for sharing this. So that was my last question. So congratulations again for your role.
Thanks.
Thank you very much for the questions. So before giving the floor to your advisors, I will ask a few questions. I will try to be quick. It's not my forte. Okay, so I think well, so your work is really impressive. I'm very happy to be here. So thank you all for inviting me. So this is not my area of expertise, although I do know the problem a little bit. It's quite funny because the question from Maxime about variability with medical images rings true. So yeah, it's really interesting, and I think the main drawback, but it's quite normal because your work is quite pioneer, is that at the end we would like a kind of clear recipe that we could industrialize or whatever, about what to do to spot and to mitigate this deep variability. So I think it's quite clear from your answers and from your presentation where we should look at, but I think your work would gain impact if you could somehow have this kind of recipe, like you should try that, and then you should try that, and that would really help.
I can provide our methodology, but maybe we have to change the way we work to show the effect of the variability in an industrial process. And there we are focusing on one layer at a time. Maybe we have to benchmark all the layers in a more online manner, and it's not the same to show the existence of this deep variability and to say now I want to capture it in a concrete scenario, in a more online phase, I would say, with real user waiting for the results. So there are first two different methodologies there, one for exploration and research and one for the industrial part. For the research part, I believe I have no regret with our current methodology. And for the production phase, both different layers, and when you find an interaction, document it, but I don't have a current methodology right now to ensure that we are not forgetting an interaction.
I'm not sure you could have. So this was the end of my question. At the end, it's very important the work that you did, really. But each type of data, each type of software, each type of hardware, everything that you have as a layer in your deep stack here has a huge possible space of variability factors, and I'm not sure that you could have some kind of systematic recipe, but the recipe would need to be adapted to every possible use cases, probably. And I'm not sure you can actually make it as a tool where you press a button and
What we can show maybe in exploration is that some layers are not interacting. You can say we can kill their variability. So that would be a nice result actually, to have a non-result in terms of deep variability, because we could say for every future case I can kill this layer, this is not a problem. And but maybe the way to proceed is to do a bit like to extend a bit what we've done in terms of scoring input sensitivity, and to generalize that to the different layers. And of course we cannot close everything, you're right. It's too much, there is too much, but we can provide some indicators. So browse all the layers, like I was saying before, and compute different scores to give the effect of this layer currently. And if you understand that this score is really high, so your layer is problematic, then okay, you have to maybe to have a model saying you need this amount of additional measurement to ensure some kind of stability. Are you able to measure that, and can you afford it?
Okay, and so to continue with a question that is more in my comfort zone. So you're using machine learning techniques that are working very well on tabular data, and so you're not using deep learning because it doesn't work that well on tabular data. And the thing is, on each layer, you could have variability factors that could necessitate different type of machine learning techniques. And I was wondering so this is something I told Mathieu, oh, I think I have an idea. Why not having some kind of meta model that would combine different machine learning model on each layer with their own specificity. So for some of them, for example, it's better to take into account the sequence, like if you're looking at actual codes. And for some of them, it's better to, I don't know the name of the hardware or whatever. And so the kind of data that you're going to deal with is completely different, maybe. And this is maybe one way also to make it a little bit more generalized. I cannot say this word. More general. No. You can generalize more. If you make it a bit more modular, okay, so this is how I would treat this kind of layer and this kind of layer. Maybe that could help.
So bring the variability in the pipeline machine learning use.
Yes.
And to say this layer requires this type of machine learning. Yeah, it's very interesting and actually, So to provide a way to search for different architectures according to the specificities of the different layers and to combine that into a very nice pipeline. It's very interesting.
And also you could use your sensitivity score to weight each models according to how sensitive the layer is.
So as an external parameter, I don't know how you deal with that.
Well, usually you learn them. In machine learning, we learn everything. It's easier.
Yeah.
But you could actually not learn them and use this kind of score to do that, maybe.
Yeah. Okay. Include that as part of the function deciding which.
Yeah.
Yeah.
Whatever.
Very nice.
Food for thought.
Yeah. Thanks for sharing.
Okay, so now I will give the floor to your advisors, starting from Arnaud, maybe.
Okay, thank you. I will not have any question. Just want to thank you for these 3 years working with you. It was a very great pleasure, honestly. Just a little bit of context, maybe. You faced the pandemic during your first and second year. And during the pandemic, you faced also many paper rejection. So you show very good resilience. So it was to be noted. And I really like your presentation. I think it's at a very good level of abstraction for non-experts. It explains key points, and for experts, it provides very good scientific contribution. So thank you for these 3 years again, and congratulations, and good luck for the next steps. That's all for me.
Okay, thank you, Arnaud. Mathieu, if you want to continue.
Okay, nice warm up. So I know Luc, I know you since a couple of times. We met each other at NSAI for software engineering course, and then we have a data science project and on 21 videos, only 21 videos, and so we made you made huge progress. You really advanced this concept of variability. It requires to master many skills like data science, machine learning, software engineering. So congratulations for combining all these things. Congratulations also for opening new research direction. Like all the questions we have, I think it's because this deep stuff is a bit mysterious. And it also impacts the way we are doing science. Because, for instance, in medical imaging, we have to tune several parameters. And what about the generalization of our scientific results? Also, thanks for your contribution to the team, the diverse team. awesome. You help many people, not only at the work level, right? So that's great. And also one thing I would like to highlight is your really incredible work about reproducible science. So when you write a paper, sometimes you need more information, right? You need to correct a sentence, and you say, okay, I need to know more about this. And with Luc, it's simple. You just open the notebook that he provides you. He even points out the exact lines of code. I think he made even that for the presentation. He puts links inside the slides, and it points out to, to the direct source. And then you can review the data, the results, and so on, and have extra amount of information. And I think it's a bit underestimated in his contribution, but that's really awesome. And I'm soft with that. I encourage all people to have a look at all the notebooks made by Luc. I think that this is the future of science. I also think it shows you all your qualities, skills in data science, skills in communication, rigorness. So thank you very much. It's incredible. And I spent a lot of fun with you. And yeah, see you in the future.
We hope. Okay, thank you.
Okay, there is not much left for me to say, but I would also like to congratulate you for this huge amount of work, and to even add over what my colleagues said, I would like to stress that what I appreciated was your always very positive attitude in difficult times, and because each time you got feedback, even when it was very negative, you always took it positively, which is a big quality, saying, okay, I understand this point, and I'm going to address it this way. And I think this is a very strong quality of you to always see the positive side, even of very negative comments. So congratulations for that. And the second point, I would like to even enforce what Matthew has been saying about your very scientific spirit, in a sense that this work has been as a huge experimental side, and experimental computer science is difficult, and you handle that in the right way by making sure that everything was reproducible. Behind that, there is a huge amount of work. You cannot imagine how much data is there, how much system has been. I mean, you can see just this list here about the number of systems with so many options, so many situations, so many data to handle, and done that in a way that is reproducible. And that's the real challenge of modern science, to make it right, not just, running some experiment and then providing some data that nobody is able to reproduce. Here, everything is reproducible, and that's a huge performance. So I would like to stress this point that you during all these PhD theses, you always had the right mindset of a real scientist. And for me, this is something that is very, very important when you want to be a doctor.
Okay, so yes. Are there questions in the audience? So only people with a PhD degree can ask questions. That's Nope. Okay.
Thank you.
Okay. Thank you. So you will have time to say something. I know that probably you want to, but we need to first discuss together. So I don't know how it works. Are we leaving? We stay here?
No, we stay here.
Okay. Sorry, in about 20 minutes, you can come back. question and answer session raised very rich exchanges and discussions. You managed to answer both technical and higher level questions of the committee, showing your deep understanding and maturity on your research domain, but also on related ones such as artificial intelligence. So for all these reasons, this is the moment, the jury unanimously wants to deliver you the PhD degree in computer science from Université de Rennes. Congratulations. So now, as a new PhD, you have to read a statement about how you're going to be a scientist in your future career. So I let you do it.
En présence de mes pairs, parvenu à l'issue de mon doctorat en informatique, et ayant ainsi pratiqué, dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique, dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Congratulations again.
Thanks. So I would like to congratulate a few people. So first to the jury member, so thanks for being here. Thanks for your ideas and questions about my presentation. Thanks for your interest. Thanks, Lisa and Rick, for your very clear report about my manuscript. I modified already the manuscript thanks to you. I want to thank also all the people here in ERISA, the administrative staff, the people allowing us to do our work, and of course the diverse team, which is basically here. So thanks to you, thanks for the discussion during coffee and after coffees also. Thanks also to the RESIST associate team in Simula, and especially Arno Gottlieb and Helge Spicker. And finally, thanks to my co-authors and especially referee supervisors. So this thesis won't be without you. And, thanks a lot for that. And finally, I will switch for my family. Merci d'être venu ici. Et ils iront un peu dans la salle d'à côté. Donc, merci à tous.
So what you miss at distance is that now he's offering a drink in the...
Actually, you had to be there, sorry.
Cheers. Congratulations. Very well done.
Thanks a lot.
So thank you again for being here, and we will switch off the video now.
Okay.
Congratulations.
Congratulations.